Here we are back, continuing from the previous lecture, and what we have here is we're moving towards implementing subroutines. So the idea here, when we execute a subroutine, we jump to somewhere else, but the idea is we need to know where to jump back to. And so what we're going to do here is store the return address of where we need to jump back to in a register. Okay, so it brings up some issues because we only have one register, which means we can't have a subroutine that calls another subroutine without putting some extra effort into it. Okay, so remember the place it jumps back to is on the return from a subroutine is the instruction after the call instruction. So in any time in any hardware I've ever seen, any computer hardware, they always have a stack. Okay, so a stack sounds pretty amazing. It's not. It's just a chunk of memory, and it's a chunk of memory that has kind of special rules on access. And so yeah, so essentially the rules fall into the category of an abstract data type, but it's just memory. Memory is just a place where I store things. So I'm storing things, and on this abstract data type, which by the way is just some type of thing out there that I describe the way it functions. I don't have to give details about implementation. I'm just describing how I interact with this object. Okay, so what I'm going to do here is it's a piece of memory, so I'm going to read it and write it, but it actually has special terms here. So when I'm writing to this memory, it's referred to as a push. So I'm pushing something on the stack. When I'm reading from this memory, it's considered a pop. I'm taking something off the stack. And so these terms are just, we use them over and over again forevermore, so we'll get used to that. So there's also the notion of the top of the stack. The top of the stack is the most recent thing I put on the stack. And there's also a notion of a stack pointer. Now, a stack pointer essentially points to the top of the stack. And so I think it's very much more clear than it in hardware than it is in software, but we need to look at kind of both implementations. So this is a software-based stack. And the idea here is, and here we got an empty stack here, but what I'm going to do is I'm going to push one thing on the stack, and I'm pushing the value of 34 on the stack. So this becomes the top of my stack now. Once again, the top of the stack is the most recent thing I pushed onto the stack. There it is. Okay, so I'm going to push 3 more things onto the stack. And what it is this is the first thing I pushed. The 3 other things get pushed underneath it. Okay, so looking good. We'll just go with that. But the interesting thing happens is when I pop something off the stack. So the notion of a stack is referred to as a last in, first out. So the last thing I put on the stack was 17. It's going to be the first thing I take off the stack when I pop it off the stack. So I'm popping the 17 off the stack. Here's my new value right here. The top of the stack is still the most recent thing I put on the stack, after, of course, pulling something off the stack. The other notion here is I'm taking 2 more pops here. And this is the first thing I put onto the stack a long time ago. Now, this is a classic software implementation of a stack. We don't typically do that simply because we're working with hardware. In hardware, this would be very inefficient because every time I pop something off the stack or push something on the stack, I would have to rewrite all these values. Even though I'm pushing one thing on the stack, I'd have to rewrite the whole stack, which would take way too long. And so this is not a good hardware implementation of a stack. A better idea would be this version right here, which would be a software implementation. So the idea here is I'm pushing a value onto the stack, that same 34, but then I have a stack pointer. Stack pointer is just going to be a register, it's going to be the address of the top of the stack. So you can see the 7FFF here. Hopefully you can see that. It's probably not, but that's the value of 7FFF right there. So I push one thing on the stack. What I do is I decrement the stack pointer. The stack pointer is decremented for no other reason except that's just always the way it's done. So here's the notion of putting 3 more things onto the stack. I'm pushing 3 more things onto the stack. The 17 is the last thing I put on the stack. So what I'm going to do is decrement that stack pointer 3 times. It's now, here's 7FFC. It's pointing at the most recent thing I put on the stack. All looks good. Top of the stack is right here, of course. So I'm going to pop one thing off the stack. So that means, essentially, I'm going to take this value, copy it to somewhere external to the memory, and I'm going to adjust the stack pointer. And what happens here is I don't have to actually physically take that off the stack. What I need to do is just adjust the stack pointer. So when I'm doing one pop or one push operation, I don't have to adjust the entire memory as I kind of would in the software-based implementation. All I do is adjust the stack pointer. Okay, and so here's, once again, I've popped 2 more things off the stack. Everything is still on the stack, but I'm considering this value down here to be the top of the stack. If I were to push another thing onto the stack right here, it would actually overwrite this value right here, and I would lose that value, but that's no big deal. So once again, I'm going to write this again. These are considered last in, first out. So the last thing I pushed on the stack is going to be the first thing I pop off the stack. So once again, this is going to be our hardware implementation of the stack. So in looks good, RISC-V, typically we're going to use x2 as a stack pointer. X2 is also known as as SP. It's a alternate name for the stack. Typically, we're going to use that because it's actually something. Okay, so in the end, we are not going to use either X1 or registers X1 or X2 for anything, because X1 is typically going to be our return address. X2 is going to be our stack pointer. We don't want to mess with those. Our program has 1 stack pointer and 1 return address. We don't want to mess with those. Typically speaking, when I start my programs out, initializing any program, I'm going to set the stack pointer to a known value. Remember, keep in mind that the stack pointer is the top of the stack. I can put it anywhere in memory. Typically, if you look at the memory model for our RISC-V, it actually sort of kind of sets aside some area of memory for the stack. Certainly, we want at the greatest value there, that's where we want to start the stack. Remember, the stack, for some reason, grows back. So it grows from higher address values to lower ones. So I'm going to put the stack pointer at the maximum value of the stack. So once again, it's customary. That's the way it's always been done. No one questions it. If you don't like it, you can change it for your computer that you design. So it turns out it's pushing and popping is just a super, super important operation in microcontrollers, but it turns out there's no push and pop instructions in RISC-V. So it's really kind of uncomfortable at first, but it's something you can get used to real fast, particularly if you haven't seen a push and pop instruction. So all you get in the RISC-V architecture, only thing you can push onto the stack is a register. You can't push a memory value onto the stack. It's not possible with the instructions. Okay. Additionally, the only thing you can pop off, you pop something off a stack, the only where you can pop it into is a register. So the push and pop operations are register based, which is essentially read and write operations, which is no surprise because we're going to implement those pushes and pops with store words and load words, which are essentially memory access instructions, which makes sense because the stack is going to be implemented in memory. So once again, when I push something on the stack, I'm essentially storing it on the stack, which is going to be a store instruction. When I pop something off the stack, I'm actually loading it into a register, which is going to be a load type instruction. So those are constants. Those don't change. Pushing, like I said, pushing is going to be memory write, which is a store word. Popping is going to be memory read, which is a load word. And I'm thinking this is getting kind of long, so I'm going to go ahead and stop that here. We'll call this the second lecture, and we'll come back at this point in the next one.